Let n be a very large integer written in binary. Find an algorithm which computes the greatest integer function of square root of n in big of log cube of n bit operations. Suppose that the given number n has k plus 1 bits. As a first approximation to the square root of n, consider a number formed by taking 1 followed by floor of k by 2 zeros. That is, our first approximation will be of the form 1 0 0 etc 0 0 0. Here there are floor of k by 2 zeros. So this first approximation is a binary number containing floor of k by 2 plus 1 bits. Now we find the digits of m. For this we find other approximations, better approximations to m, going from left to right after the 1 here. Each time we try to change these zeros to 1 and consider the new number and then square it, and we will check whether the square of that number is larger than n. If it is larger than n, we will put that 1 back to 0, so that our second approximation will be 1 1 0 etc 0 0 0. Here we have changed this 0 here to 1. This will be our second approximation if the square of this new number is still less than or equal to n. Otherwise, we will take the second approximation as this number in the first approximation itself. Similarly, in the third approximation, we will be trying to change this third digit, that is the third digit from the left of second approximation, to 1, and we will try to square it, and we will check whether the square is less than or equal to n. Otherwise, we will assume that the third approximation is also equal to the second approximation, this number itself, and so on. Thus, we can see that squaring the resulting number in each approximation will require at most k by 2 plus 1 whole square bit operations. That is because the numbers involved in each approximation contains at most k by 2 plus 1 digits. And we can see that at most k by 2 such multiplications will be done in this process of finding square root of n. Thus, the total number of bit operations required will be equal to number of multiplications required into number of bit operations required in each multiplication. So this function can be expressed as big of k cube. Since we know that k is equal to big of log n, we must have big of k cube is equal to big of log cube of n.